In our last video, we discussed what were the rules for significant digits. And so one of the things that usually pops up within students' minds is, why do we care? Why do we need Sig Figs? And really what that's going to come down to is two answers. One, we kind of already addressed. Significant digits give us information about the device used to give that measurement. So it's kind of an important observation. So that information gets implied within the number itself, and we don't have to specify that it was measured using a ruler manufactured in Boston, making stuff up. Okay? But the other part of it is going to come down to how we use those numbers. Because more often than not, within science, we don't just take a measurement, we try to do something with it. We run a calculation. When we run those calculations, we have to ensure that we don't add more information or remove information from the measurement that we took. Okay? And that can become kind of challenging because it depends on the operation we're doing, the mathematical operation. So if we look at addition and subtraction, our rule when it comes to Sig Figs is that our result is only as precise as the least precise measurement, which I know is a lot, so let's take a look at an example. If you were given the calculation there to run, we would go through and attempt to add that up. And if you were really good at math, it takes a little bit of practice to do it this way, but you can just run this out because, you know, let's just say that I was that good and we come up with that number because we're that good at adding things up. You might say, well, isn't that the answer? No, well, no, it's not. According to science, the answer means that I run that calculation and then I have to take into consideration my significant digit rule. Right? And that says that my answer is only precise as the least precise. Right? Well, that first number is only precise to the tenths place. The second one goes to the tenths, hundredths, thousandths. The last one goes to some precision that I can't even label. Okay? Which means in our answer, we can only report to the tenths because that's the one that is least precise. So I go to my answer, and my answer becomes not 115.63362, but 115.6, and in this case, grams. And what usually happens is that people flip out and say, well, didn't you just delete information? You just deleted the information of that 3, 3, 6, and 2. And I would argue, actually, no, I didn't delete it. By you including it, you've actually added information that wasn't there. Right? And that becomes kind of a confusing question that if my technology actually connected, we would actually move on and see. Okay? What you are assuming when you write those numbers is that you have a bunch of zeros in here. But remember, based off of our Sig Figs, I don't know what those numbers are. Those are question marks. They could be zeros. They could also be nines. And if they were nines, how does that change my answer? Okay. Well, again, we pull out our awesome math skills. 115, did a little bit of practice with this. 7, 3, 4, 6. And I'm going to guess I screwed something up there because I think I'm missing a place. 0. Okay. The original number that we started with, which is where you assumed that there were zeros, was 115.63362, because my memory is so great. And if we now compare those numbers are definitely not the same. If we go through and look and make raw comparisons between them, we'll note that in the hundredths place, they are both 1. In the tens place, they are both a 1. In the ones place, they are both a 5. So those numbers would effectively be our obvious digits from a measurement, guaranteed values. We move to the tenths place, and we're now either a 6 or a 7. There's our guess. That number varied at the tens place. Because it varies there, I'm now guessing. If I report any other numbers after that, those are guessing on guessing, and that would therefore be bad. Okay, so I can only report out to that tens place. So I could go through and say, well, I'm going to test both calculations, and wherever they vary, that's where it's going to be. Or somebody's already gone through and done that for us and noted an interesting rule that where it varies happens according to the precision. Okay? So when you do addition or subtraction, because they're ultimately doing the same type of calculation, just opposite directions, it's based off of precision of your number. Okay? So that precision is when we stop reporting decimal places. So for this first one, okay, if we're looking over here, that one reports out to the tenths place. That next one we said goes out to the thousandths, and that last one, tenths, hundredths, thousands, 10,000s, 100,000s, I think, goes to the 100,000s. For those of you kind of asking the question about Sig Figs, you might say, well, the blue one has more Sig Figs. How come that doesn't matter? Well, that doesn't matter because of how the operation works, and it's based off of the precision of your measurement, not the number of Sig Figs, which is a common misconception, and we'll see why that's a misconception in the next slide. Okay, so our rule is not number of Sig Figs for addition and subtraction. It has to do with the place, okay, the decimal place. Why would people get confused about Sig Figs, okay, or the number of Sig Figs? Well, are there other mathematical operations like multiplication and division? And if we go through and look at the rules for multiplication and division, you'll notice the rules change. Okay? Again, why do they change? They change because you're doing a different mathematical operation, which changes how you have to report your numbers. How do we decide what that rule is? Well, we do the same thing that we did in the other case. We take our numbers and we do a multiplication. In this case, if we wanted to find the area of the square, length times width or height, however you want to call it, the number that a calculator would spit out is 33.488 units squared. Okay? But to run that calculation, what did I assume? I assumed that that was a 0. Okay? That could have been a 9. And if it was a 9, this would have been the number that it would spit out. When we go through and compare these two numbers, in the tens place, it absolutely comes in as a 3. Okay? The next place, it changes. There's our guess. So we are guessing with that very next number. Okay? Because the 4 comes from an arbitrary statement of it being a 9, I don't know that. The only information I've got is that there's nothing there. So we would report it as a 3, and that is now my guess. I can't report any more numbers. Keep trying to write the word guess. And then this would be obvious. If we tried to compare this back to our addition subtraction with the precision of the place, that doesn't work because our answer varies at the ones place, but both of our numbers, our measurements, report out more information in the ones place. Okay? So with more testing of this, what we end up discovering is that our rule changes, and it's now not based off of the precision of the number, but the raw number of Sig Figs. 7.28 has 3 Sig Figs. 4.6 has, 2 Sig Figs, which means my answer needs to be reported to 2 Sig Figs, and there you go. That's why we had to report 33, okay, with no other numbers. Okay? So the rules that we've got are kind of not an artifact, sort of an artifact of the calculations of checking these things out and seeing where that variability comes in. They aren't just, well, let's just make things up. The operator changes it. Are there other mathematical operators? Yes. If you switch to those other mathematical operators, does it change how we convert and move Sig Figs through? Yes. How would you decide what that rule was or determine it? You would test it, okay? Because somebody's already been doing this for a very long time, those tested observations have already been done, and so all you would do is look it up. Why do you need to memorize addition, subtraction, multiplication, division? Because those are the mathematical operators that you will be using frequently in this chemistry class and your subsequent chemistry classes. But if for some reason you had to do logarithms, right, or angles, do calculations with angles, each of those operations have new sig fig rules, and you would have to look up those significant figure rules. Okay? So, last thing that we really got to drop in here is this concept of rounding. My least favorite concept or discussion, because everybody does it differently and it doesn't usually make a significant enough difference to matter. Okay, so we're looking at maybe 10% of all your calculations having to really worry about this rounding thing. Okay, because it's such a small number, it's either up or down, you then 10% and you've got a 50-50 chance of getting it right, you're down to 5% of the time you're wrong, also known as 95% of the time you're right. So do we really care? Okay. It's officially part of it, so let's take a look at it. If we're looking at it, addition, subtraction, we got another example. When we add those two up, we're only allowed to report to the hundredths place. We look at that next number. If that number is 5 or larger, we add 1. So our calculation becomes 1.34 grams. If we do multiplication division, 2 sig figs versus 3 sig figs, I'm only allowed to report out 2. That 5 is my first insignificant digit because it is 5 or larger. I will add 1 and my number becomes 37 units squared. Right? And so that's how we can run through our rounding. Right? So there we go. We've got my version of the rules here. It turns out that that's not perfect and that there are variations of this rounding scheme. Right? As long as you're consistent, it's okay. Just don't start making stuff up with your rounding. It is something I'm very cognizant of and try to ensure that those kind of rounding issues don't show up in exams. I can't guarantee that, and I certainly can't guarantee it in future classes. Okay, so be aware that rounding can mess with your systems. Watch out for it when you run your calculations. Okay, so we got a little bit of practice here. We got 6 questions, 1, 2, 3, 4, 5, 6. Go through and attempt these as best you can. So this would be your opportunity to hit that space bar, click, do whatever you got to do. Pause the video and attempt a few. And because I wasn't 100% sure that I believed that you paused it, here's a quiz question. And now we can kind of talk about it. There might not have been a quiz question, actually. So now we can go through and take a look at these. We're looking for sig figs. The 1 and the 2 are guaranteed sig figs. No decimal, which means I need sig figs to the left and right. So that first 0 left, I have a 1. To the right, I have a 2. That 0 is significant. Move to the next 0. I look to the left. That is significant. I look to the right. I don't know. Right? Is there a significant digit anywhere out there to the right? No. That's not a significant digit, which is then going to mean that 0 is also not significant. We would get 3 sig figs for this. If we move to question 2, 1, 2, left, because there is a decimal point, so we do have a decimal in this case. If there is a decimal, all I need to do is look to the left. Yes, so that is also significant. Left, yes, that is significant. Left, yes, significant. Left, yes, significant. 6. Sorry, it took me a little while to count that out. Okay. Doing all of our calculations here. Dang it, I forgot my freaking calculator. I can just tell you the answer because while I did forget a calculator, I did kind of code a backdoor in this for myself. And that if we added all those up, the answer that we should end up with is 129.04 meters. Right? Your calculator, I believe, throws on a bunch extra numbers. You have to cut it off at that 4 because when we're going through addition, we can only report to the least precise place. This one goes to, what is that? 1,000, tenths, hundredths, yeah, thousandths. This one goes to hundredths, and this one goes to our thousandths. Again, so hundredths is the last place I can report to, 129.04 meters. Okay. Next one down, multiplication. We multiply that out. If I remember correctly, I think you get 4, 5, 3, 9. Number. Let's just call it 8621. I honestly don't remember those numbers. Okay, but the important part is recognizing our sig figs. 5 sig figs, 3 sig figs, 6 sig figs. Multiplication division, I'm only allowed 3 significant digits, 1, 2, 3. This number, larger than 5, so I add 1, and I now get 4, 5, 4, and now becomes usually the dilemma. Okay? If I just leave it as 454, this is 454, as opposed to this number being 4,500. 390. That's a pretty significant difference. If you were expecting a $4,000 paycheck and your boss gave you a $400 paycheck, you'd probably have some choice words. Okay? So how do you ensure that you don't lose that information? Well, put in the 0. And if you include a decimal point, though, that 0 now becomes significant, which would say 4 sig figs, we're only allowed 3. So how do you ensure that you only get 3? Don't include the decimal, 4540. And you now have the appropriate measurement. That 0 is insignificant because you haven't put in a decimal point. What happened to the m's? Well, you just multiplied m by m by m. You aren't canceling it, you aren't deleting it, nothing like that can happen to it. So it just multiplies out and you get m cubed. Some people don't like this, and this is one of the reasons why we invent something known as scientific notation, which we'll see in a little bit. And you could write it in scientific notation. That removes the question of the 0 altogether. Okay, so both of those are valid ways to write or report that number. Whoops, wanted the eraser, clean that all up. If we continue on, that subtraction becomes another kind of interesting one to observe, because if we run that, we get 0.03 liters. And why does that become a weird one? Well, it's addition and subtraction. We can only report out to the hundredths place, so that's what we've done. How many sig figs in our starting number? 4. How many sig figs there? Was that 6? How many sig figs in our answer? Only 1. Addition can result in more significant digits. Subtraction can result in the loss of significant digits. Okay? This becomes a big deal because you're now losing information. If we look at that number, 0.03, the only digit we've got means if we look at our measurements, we're allowed an obvious and a guess. That's it. If I only have one number, it's a guess. My whole calculation is now hinging on a guess. Right? That's an awful system to be in, which means if you're ever doing an experiment where you think a subtraction is going to be necessary, you usually try and make sure that the difference between those two things, so the difference between blue and the difference between red, that those numbers you want to make as large as humanly possible so you minimize the loss of significant digits. Right? So that's an experimental kind of artifact that we can address when that would be important here in a second. The last one is just a division. I don't remember this one having any particularly weird oddities with the calculation, but I could be wrong. 0.0454. The part that one's there for is just like the multiplication. The units don't disappear. We would have grams over centimeters cubed. Right? And that ends up being our answer. As far as significant digits, it is division, 3 sig figs. That ties to our 3 sig figs in our number as opposed to the 5 sig figs there. Okay? How important are sig figs? So usually at the end of this, people just freak out and just don't want to deal with sig figs anymore. They really aren't that big a deal. When it comes to our calculations, we pretty much just run 3 sig figs. So if you default to just reporting 3 sig figs, you're probably not going to have any issues. I would bet you're in kind of 80% correct. If you end up having to move into a science or engineering field, significant digits are insanely important, right? And you need to watch out for them. Though if you move into those fields, you usually also try to ensure that the instruments you're using all have the same precision so that when you do calculations with them, you don't run into significant digit issues. Okay? So there's ways that you can kind of control your environment to prevent that, which really means the only time you have to stress about significant digits is in a science class. And as best I can tell, it's in a chemistry class, because biologists hate numbers worse than organic chemists. I'm an organic chemist. And physicists just ignore the whole issue as best I can tell and just don't worry about it and just say, report whatever you feel comfortable with. Chemists seem to be the only ones that really seem to lock down and care a whole lot about it. Depending on where you go in chemistry, it may be a bigger issue or not, and it's usually only in lectures because the labs kind of self-resolve you're using that equipment. Okay, so just kind of be aware it is an important topic, but I don't let it consume, might be the way to think about it. Okay. So with that, I think it might be useful to have it all on one slide. So here we are, slide 15 in our slide deck has all of our significant digit rules, how you would go through and use them, multiplication, division, and the rounding aspects. One place. Feel free to print that out and have that handy whenever you go through and do homework or, for that matter, exams. And with that, we're at the end of this video too. So I hope that went well.